So, today we will discuss about density of states of 3-dimensional electron gas. So, density of states is defined as the number of orbitals per unit energy range, number of orbitals say it is n per unit energy. So, if n is number of orbitals, then dn by d is defined as a density of states. Okay. So, what about n? N basically we have taken earlier that number of electrons in the system. So, total number of electrons in the system and number of orbitals will be half of that, right, because in each orbital 2 electron can stay, one is spin up and another is spin down. So, basically n by 2 or number of orbitals, but if we consider that degeneracy, what is degeneracy and non-degeneracy in quantum mechanics? So, we have energy levels where electrons stay. So, this we tell this electronic state also. So, when here 2 number of electrons are staying, then these 2 electrons will have the same energy, but these 2 electrons have different quantum numbers, otherwise they cannot sit in one energy level. Okay. So, depending on the quantum number, so the states of these 2 electrons are different, although energy are same. Okay. So, this we tell is degeneracy. So, we can take these 2 states, 2 energy levels, but they have same energy. So, then we can tell this each energy level having the 1 electrons. Okay. So, that way here that number of electron and number of orbitals. So, now in that sense we tell the number of orbitals are n. Okay. So, there quantum number will be different for each electron and for each level, although energy may be same. When the energy of electrons are different in different states, so then we tell this it is non-degenerate. Okay. So, degeneracy, number of degeneracy or fold of degeneracy, twofold here, twofold degeneracy means 2 states, 2 particle, 2 electron have two states, but same energy. So, degeneracy is twofold degeneracy, it may be threefold, n-fold degeneracy. Okay. So, in that sense, here this number of states per unit energy, so that is density of states. So, that is why here we have taken this number of orbitals or n. Okay. So, again we will not consider that in each state we will have 2 electron, that way we will not consider. So, we will consider each state have they are in different orbitals, but they may have the same energy, the orbital may have the same energy. So, that is degeneracy. So, why we take this degeneracy, because under some external parameter this degeneracy is removed. So, energy levels same energy, now after applying external parameter. So, this degeneracy removed means the energy levels are separated. Okay. Like in case of, if we consider magnetic material, so electron, in that case electron will have spin up and spin down. Now, if we apply magnetic field, so then this same energy initially without magnetic field, now they will be splitted. Okay. So, their separation will be, so initially it was the energy for spin up and spin down. Okay. If we apply magnetic field, this energy level splitted into 2 and the spin up and spin down are separate now. Okay. So, then we tell degeneracy is removed. Okay. Now, we will have this separate energy and of course, separate state, but here we have same energy, but separate state. So, here we are considering 2 orbitals having same energy and having 2 spins of electrons. So, I have to go back this, I need n number of orbitals. So, that we you remember that we considered the Fermi sphere of in k space, okay, and kx, ky, kz they can take value this 0 plus minus 2 pi by L, 4 pi by L, etc. right, 0 plus minus 2 pi by L plus minus 4 pi by L, right. And this all kx, ky, kz can vary, can have these values. Overall 2n pi by L, kx, ky, kz can take 2n pi by L. So, here in this case this volume of this sphere is 4 by 3 pi k square, not square, cube. Okay. And the smallest volume, it is if it is origin, then 2 pi, 4 pi, etc., 2 pi, 4 pi. Okay. So, smallest volume will be just with length of 2 pi by L. So, 2 pi by L cube. So, in this volume you will get one set of triplet set of k value k x, k y, k z. Okay. So, this will give us the total number of orbitals in this sphere. Now, if this sphere this is k f, this is a Fermi surface, this sphere surface is Fermi surface, then all electrons are inside the sphere, right. So, if you put k f, then you can write this the total number of orbitals, Okay. So, from here one can calculate n, right. So, just I will write this value. So, n you will get basically here, let me write n you will get, what you will get, this will give 8, this for this 8. So, 8 will go. So, it will be basically and pi cube 3 pi square, you will get 3 pi square and of you will get v L cube that is v basically. So, L cube that is v kf cube you will get. Yes, hopefully I have written correctly. So, kf 3 pi square n by v, it will be okay, this fine. This is total number of n electrons, and then kf will be equal to 3 pi square n by v, right. And then corresponding energy, Fermi energy one can find out, F equal to h cross square kf square divided by 2m. So, kf square you know, so it will be h cross square by 2m 3 pi square n by v, then it is square, so 2/3. Okay. So, now I have n. So, n is equal to put kf here. So, v by 3 pi square kf cube. So, this is kf. So, 3 pi square n by v to the power square 2 by 3, right. So, v by 3 pi square, yes, and but I am missing one part, that should be 3 pi square n by v, 1/3, that is correct, and that n h cross square 2m, that is also correct, e also correct, and kf is this. So, in that way this is also correct, fine. Now, actually if I put kf, okay, so this n equal to v 3 pi square and kf is 3 pi square n by v 1/3. So, this is cube, right. So, then it should be like this, okay. So, this will come is n equal to n, but that is not my aim. Actually, I understand what is the problem. Actually, in terms of energy I want to get n. So, I have to use this one, okay. I have to use this one. So, from here I am getting that E equal to this. So, n equal to so 2 m by h cross square, and then this EF is there, but okay, let me write EF, and then 3 by 2, okay, then V by 3 pi square, that is the expression for n. So, 3 by 2, it is n 3 by 2. Now, what I want to do, I want to find out density of states. This is the dE equal to dN by dE. So, this dN by dE, for that. So, whatever the, so now n is total number of electron in the system, okay, and that we are taking as a total number of states, total number of orbitals, as I mentioned this, considering the degeneracy. So, this if I consider this, okay, I think I should write n equal to 2 m by h cross square (3 by 2), then v by 3 pi square, then this E to the power 3 by 2. So, I remove this suffix f because I want to find out in general number of states at defined energy. So, here just we have used the condition that this inside the Fermi sphere all electrons will be there, okay. So, but if I take in general energy, even energy is higher than the Fermi level, So, I do not have any problem, because my total number of states, total number of electrons, okay, it is conserved, it will remain same. Now, so automatically it will come that there is up to which energy that all electrons will be there. So, that we can generalize removing this F. So, then from here you can take differentiation of this. So, it will give you 2 by, this is 3 by 2, this term 2m h cross square 3 by 2, and this term v by 3 pi square e to the power half, right. So, these three will go, and then actually I can write these two. Okay. So, this is the expression for density of states, and you can see the density of states, it varies with square root of energy. So, if I plot what I will get. So, this if I plot density of states, okay, this is energy, and this is density of states. Okay. So, what you will get? You will get basically parabola, you will get this type of curve. Okay. So, let me write up to this, So, it is there, states are there, but say this the point, this is the energy EF. Okay. So, density of states, that is it will you will have beyond this Fermi level also, but these are Fermi energy. So, this part is basically occupied by the electrons. So, this density of states varies, yes. So, now we see that this whatever this density of states, and here we have plotted it up to this. So, all electrons are just filled this below the Fermi level. So, this is the Fermi level, Fermi energy level. So, this is basically situation of down state, and temperature at T equal to 0, absolute temperature is 0. So, the ground state system, so far whatever we have discussed, and their electron is distributed like this, and this density of states I have to keep note here, say density of states d, what we got, that is that equal to 2m by h cross square 3 by 2 v by 2 pi square E half. Okay, E half. So here this you can see this, I can write in terms of basically, you see, if you see this EF is h cross square by 2m 3 pi square n by v, right. So it just from here it just opposite to yeah, I think here also I can say that n by here n, and this is, so if I want to write in terms of n and this Fermi energy, you can see n by EF, what it will give? N by EF okay. So this term will go, no, I think I have to basically what other way one can do, this one I can write ln n equal to, not this term, ln L equal to 3 by 2 ln E, 3 by 2 ln E, and this term is constant, okay. So this if I differentiate, so you know that dn by n log is there equal to 3 by 2 dE by E, right, and this constant, so it will go. So from here you can get dN by dE, that is nothing but density of states, equal to 3 by 2 n by E, okay. So this way also one can express the density of states. So that is why from here I was trying to get this expression. So this also one can get 3 by 2 n E, okay. So if it is so I think now I can remove this part, because I have kept the note of this. So here density of states we got. Now this density of states, that expression is very useful for our different calculation. Now here whatever things we have, distribution of electrons in orbitals, that is at low temperature T equal to 0, at absolute the temperature T equal to 0, and it is in ground state distribution. But what will happen when temperature is T is not equal to 0? What will happen? Then how the electrons will be distributed in the orbitals? That is the question. So here this density of states or this expression whatever we got, there we assumed that following the Pauli exclusion principle, starting from the lowest level they are filled up to Fermi level. So that is fine for T equal to 0, but for T is not equal to 0 there is a temperature. So what will happen when I will increase the temperature of free electron gas from T equal to 0 to T equal to some temperature, say T1, what will happen. So, this answer is for this answer we have to consider the Fermi-Dirac statistics, Fermi-Dirac distribution. Fermi-Dirac distribution, that is the basically probability. What is the probability of an electron to stay at a particular energy state when temperature is increased to T equal to 0 to T equal to some temperature. Okay. So, this Fermi, so to know that distribution, that is the to know how to know that distribution at higher temperature, then this Fermi-Dirac statistics, Fermi-Dirac probability, Fermi-Dirac distribution is the valid one, and that is 1 by exponential E minus EF by kT kBT Boltzmann constant plus 1. Okay. So, that is the Fermi-Dirac distribution. So, if temperature exists for the system, it is not at T equal to 0, then following this distribution one has to find out the electrons in different energy levels. So, from here you can see that when T equal to 0, so this is infinity, right. So, this denominator is infinity. So, 1 by infinity is 0, right. So, when T equal to 0, this F1 is 1, Fe is 1. So, for what we are getting for T equal to 0, F plus distribution F equal to 1, right. So, that means is it correct? Yes. When it is 0, so that is infinity. This is 0, so this infinity, exponential infinity, infinity, so this will be 1, fine. Now, when T is not equal to 0, that will come. So, for T equal to 0, when so then Fe is 1, fine. And now, if I consider for T equal to 0 and E is equal to F, so this the so 0, here it is 0 by 0, so is undefined, right. So, it is the signature of discontinuity, curve will discontinue for such case. Okay. And when E is not equal to F, E is less than F, below the Fermi level. So, it is negative, right, it is negative some value, right. So, it is like this exponential will be like say e to the power minus del E t by kBT, right. And when E is greater than Ef, right. So, this E is greater than Ef, so this will be positive quantity. So, not minus, so del E by kBT. Okay. So, in this case for T equal to 0, this is infinity, So, this is infinity. So, I can write this one 1 by e to the power del E by 0 means infinity. So, this term will be infinity. So, 1 by infinity will be 0. 1 by infinity will be 0, right. So, this term will be 0 plus here 1 is there 1 by 1. So, in this case this Fe you will get 1, right, and for other case it will be 0 for other case because this plus, right. So, this will be infinity. So, this infinity plus 1 sorry okay. So, for t equal to 0 this is infinity. So, e to the power infinity is infinity plus 1 infinity 1 by infinity is 0. So, this part will be for this case F e will be 0. Okay. So, this is telling at t equal to 0, I think this not right statement, I think this is the right one. So, here you can see that when temperature below, not temperature, this energy is below Fermi level. So, probability of filling these orbitals with electron are 1, that is the maximum probability, and this when it is above the Fermi level. So, this it is probability 0, that means there will not be electron above the Fermi level. So, one can draw this distribution, it is like this. Okay. So, this is basically E and this is Fermi distribution. So, maximum value is 1, okay, and 0. So, as I told that when E equal to F there is a discontinuity, when E equal to F there is a discontinuity. Okay. So, this is a discontinuity. Okay. Now, when temperature increase, so it is not T equal to 0, T have some value. So, what will happen from here? You can show that this curve will be like this. Okay. For other temperature, curve will be like this. I think it's not that. Okay. So, these are higher temperature. So, basically this part is telling that this electron will be removed from here and occupied in this place. Okay. So, from here easily you can explain this. Okay, this one. So, all the time for any temperature, when E equal to F, this is 0, So, so exponential 0 is 1. So, 1 plus 1 2. So, 1 by 2. So, here this value, this is basically this probability F e is half all the time for all energy. So, this important fact, and if temperature is such that, so depending on temperature, if temperature is so what we are seeing, the electron when increase the temperature, electron are going to the excited level, okay, from where, near the Fermi surface. So, temperature is higher and higher, then it is going deeper and deeper. So, so this energy, when temperature is such that electron will be excited from here also. Okay. So, lowest energy level. So, in that temperature, so this basically we write Tf Fermi temperature and kBt, this energy will be such that this it will be equal to EF. Okay. So, when this temperature is such that when KBTF is equal to EF Fermi energy, so this temperature is called Fermi. So, these are basically we take as a reference when temperature, whatever temperature we take, so it is greater than TB, TF, or it is less than TF. Okay. If it is less than TF means electron will not be excited from here. So, it will be this side. When it is greater than TF, so electron will excite from here also. So, it will go like this also, right. Okay. So, these are the significance. So, I will stop here, I will continue in next class. Thank you for your attention.